Okay, chapter 15, day 1. It's kind of a short chapter. It starts out with conditional probability, which is similar to what we did earlier in the year in chapter 3. Conditional probability is the probability of something happening given the fact that something else has already happened. So it's a conditional situation, all right? Symbolically, we write it this way, where this little bar means given, and I think we talked about that earlier in the year. So this would be read, the probability of A happening given that B has already happened. And that's how we write it, the probability of A given B. So conditional probability always is about something else happening first, and then the probability that something happening is then after that. The formula for conditional probability is the following. The probability of A given B is equal to the probability of A and B divided by the probability of B. Now, most of the time we use this formula with a table. And you can see this is found usually from a table. It's the intersection in the table like we did with chapter 3. Or it's given to you in the problem. It will tell you the chance of A and B happening right in the problem. When you set up the formula, whatever letter is here in the given that this has happened, that letter also then has to be your denominator, because it's given that it's happened, or out of the fact that that has already happened. And that's the same thing that we did when we did chapter 3. So if we take a look at page 38, number 18. Page 38, number 18, deals with liberals, moderates, and conservatives. It's that same table we used from chapter 3. And we had females and males, and there was a table about whether they were liberal or moderate or conservative. So if we wanted to find the probability that someone is female, given that they are liberal, female given liberal, and so we can let any letters that we want be female and liberal, but I'll just use F for female, L for liberal. So the probability that it's female given, that's what the vertical line means, liberal, is, now right from the chart, female and liberal, that's what the symbol means. Again, this means and. That's what that upside down U means. So female and liberal divided by the probability someone's liberal. Well, what's really nice about the chart is female and liberal is 35 out of 192. Liberal is 85 out of 192. But since they're both out of the same total, we don't even have to write the total. When we use a chart, just put in the numbers. Female and liberal, 35. Okay. Liberal, 85. And there's your conditional probability. The probability someone is female, given that they're liberal. Given that they're liberal, the chance that they're female is 35 out of 85. Now we can look at some things the other way. The probability that they are conservative, I know my handwriting's terrible, given that they're male. Conservative given male. So we have to look at conservative and male. Conservative and male is 21 out of male, 115. Okay? Conservative given that they're male. So conservative and male out of all the males. And you can see 21 out of 115. Probably that someone is moderate. Notice I did not say the word given, so we're back to just a regular probability of what's the chance someone's moderate. So I look at all the moderates, 80 out of my total, 80 out of 192. So That's that piece. Just like chapter 3, we can now test again for independence. I think you probably remember doing that. This is it symbolically. So again, we can check if two events are independent. And we ask ourselves the same question. Is the probability of A happening, is that the same as A happening given B has happened? And we did that earlier in the year, and we're coming back to that again. Notice this letter and this letter has to be the same, given this other thing happened. And if they're equal, then they're independent. Same thing we did before. If they're not equal, then they're not independent. So let's go back to our previous problem. Is being male and conservative independent? So look back at our chart. Is being male and conservative independent? Okay, let me get these arrows out of here. Well, if you remember what we did before, we identified conservative and male, and then set up two fractions for us. We go over, we go over. So remember before we set up this out of the total and then go over to its total out of the total? Let's take a look. Is being male and conservative independent? So is the probability of being male, is it equal to the probability of being male given we're conservative? So again, male and conservative over conservative. All right? You can set up the fractions either way you want, but you can take a look 21 out of 27, 115 out of 192, or you could run them this way, either way. Male, 115 out of 192. Male given conservative, 21 out of 27. Same two fractions we identified in our chart. So if you remember what we did in chapter 3, identify the conservative in male, circle it, and then just bam, here's your other fraction, or your other denominator, and then total out of the total. I think hopefully you remember doing that. Are those fractions equal? Not quite. Not quite. And we talked about that before. How close do they need to be? If they're pretty close, then maybe we would say that they're equal. But these are pretty far away, so they're not independent. They are not equal. They are not independent. There is an association. If they're not independent, then there is an association. So, last piece now with this chapter. Chapter 14, we did a multiplication rule for independent events. Now we're talking about a general multiplication rule. Okay? And the reason why it's a general rule of thumb is, again, the probability of A and B happening is the probability of A times the probability of B given that A happens. So if there's a situation where, like drawing cards, and you do not replace the card, then that creates an event that's not independent. So we have to take that into consideration. This is used a lot in which the events are not independent, like drawing cards without replacement. And we'll do some of those practice problems in class. You have to ask yourself, does the first event affect the next? If so, I have to take account for that as I multiply those events together. Last thing we're going to talk about are tree diagrams. A tree diagram is just a tool to use to try to help you calculate probabilities. A tree diagram is used when you have multiple events happening, one followed by the next. It's easiest to set up a tree to help calculate the probabilities. For example, a poll of college students found that 44% binge drink, which is like drinking 3 or more drinks at a time. 37% drink moderately, that's like 1 or 2 drinks, and the rest abstain from drinking altogether. So they either binge drink, drink moderately, or don't drink at all. They also know that binge drinkers get in accidents 17% of the time, and where they're the cause of the accident. They're the driver, they're the cause. Moderates will get in accidents about 9% of the time, and abstainers 0%. And I'm talking about alcohol-related accidents. So binge drinkers get in an alcohol-related accident 17% of the time, moderates 9% of the time, and if you abstain, then you can't be in an alcohol-related accident. So we have a multiple stage happening here. You first need to know what kind of drinker they are, and then whether or not they get in an accident depending on the type of drinker. That lends itself to a tree diagram. And as you can see, I set up a tree. Okay? Here's the tree that I set up. First of all, they might binge drink, they might be a moderate drinker, they might be abstaining. 44% of the kids binge drink, 37% moderate, 19% abstain. And then depending on whether or not they're a binge drinker, moderate, abstain, they either get in an accident or they don't. So a binge drinker, accident 17% of the time, so no accident 83% because they have to add up to 100%. Moderate, 37% of the time, they're a moderate drinker. 9% of the time they're in an accident, 91% of the time they're not in an accident. And again, these have to add up to 100%. Abstainers, where did I get the 19% from? Well, this plus this add up to 100. They don't get in accidents, so none is a full 100% of the time. And then with a tree, you have your final branch, right? Your final little limb. And so the chance that they binge and get in an accident, now our multiplication rule comes into play. This would be 0.44 times 0.17, which equals 0.075. That's the probability that they binge and get in an accident. Binge and no accident. Moderate drinker accident. Moderate drinker no accident. You just follow the trees, follow the branches, and see where you end up. So some questions we might ask, probably that they binge and get in an accident. Okay? Binge, accident, there's the product. Here's another question we might ask. What's the probability that they are moderate given that they were in an accident? So now we got to use our formula. Moderate given accident. I'm going to let M be moderate, A be accident. So, moderate given accident, which is moderate and accident according to our rule, divided by accident. So moderate and accident, where is that? Moderate and accident, 0.033. Okay? Accident. Well, accidents could be here, here, or here. So you're going to take, for accident, you're going to take this number, you're going to take this number, and you're going to take this number, and you're going to take all three of these numbers, add them up, and that's the probability someone's in an accident. Because accidents could happen to binge drinkers, to moderate drinkers, and to abstainers. Even though it doesn't happen there, it still has to be accounted for. So, conditional probability that they're moderate given that they're in an accident. Moderate and accident, that's the 0.033. Divided by all the ways we could get in an accident. So that's where conditional could be used with tree diagram. Last question. Is being a moderate drinker and getting into an accident independent? Okay, so now we don't have a table, but we're going to use our chart. Moderate, is that the same as moderate given they get in an accident? Again, I could have done accident, accident given moderate, but I already have moderate given accident up here. So I'm going to use my information from this previous question. So, percentage probability someone's a moderate. Let's go back up to our chart. Moderate, 37% of the kids are moderate, so that goes there. Moderate given accident. I just calculated it. If I didn't, I could redo this calculation with whatever the scenario is. But moderate given accident, I just calculated. Moderate and over accident, 0.306. Are these equal? Not in my eyes. They are not equal, so they're not independent. So you could say, therefore, there is an association, if someone wanted to know that. And that is chapter 15. Chapter 15 is about conditional probabilities. It's about using our charts again, checking for independence. We did that. That's nothing new to us. Okay? Checking for independence, still not new. Now here's kind of the new thing, the general multiplication rule. But this intuitively, you'll see how this works out with cards and stuff. You've done it before. If I replace or don't replace a card, we're going to do some in class. And tree diagrams is kind of new in terms of how we represent probability. I know you've made tree diagrams in the past. I'm not sure if you've made them in this situation before. And then we can use our tree diagrams to answer questions. So that's chapter 15. Thanks.